introduce the animation. It's actually a movie. It's a WALL-E. And the main title I want to discuss today is that could Earth really be surrounded by the space debris or not? So WALL-E is the Pixar animation and is described in the far future, roughly at the 2800. Humans have abandoned the Earth and they left some waste collecting rocket. One of them is named the WALL-E to try to improve the environment because the Earth have already been ethereal contaminated. And the story is over time, the WALL-E develops curiosity and the emotion and then fall in love with the modern rocket, but it is not my main story today. So I want to show you some part of the movie is here. Oh, no. Yeah. Okay. So this rocket is the WALL-E and grab the spacecraft, and then the spacecraft pass through the atmosphere. The most important scenario is the following part. Oh, I'm not means the cockroach, okay. It's here. While they pass through the atmosphere, there is the extremely thick layer full of the garbage, and this garbage is from some debris of the satellite or the spacecraft. So what I want to discuss today is is it real to find this kind of the thick layer and produced by the debris of the satellite? Okay, so we need to figure out what kind of the characteristic in the movie they show. So the key feature of this kind of the scenario, there are three important information. First one is that the debris appears to be stationary and concentrated at a specific orbit at altitude. And the second is that the typical spacing between the fragments is roughly in order of roughly 10 meters. This value just evaluated by eye. And the third thing is that despite the high density, it seems that there is no immediate catastrophic collisions during the movie show. So I want to discuss these three issues. So I separate hold of the problem into the several research problems and try to solve the different problems step by step. So I think we could really go into the detail. So first part is that we need to know some information about the satellite orbits. For the satellite around the Earth, there are several altitudes. I just mentioned the three significance. The first one is the LEO and MEO and GEO. They corresponding to a different height and its different range of the satellite orbits. So the different orbit environment is not uniform. For example, in the LEO is the lowest one. The collision rate should be high. I will mention it later. And the lifetime is quite short compared to the MEO and GEO. It's roughly 1 day to the several years. So I go back, because I want to know what kind of the satellites most common, because I want to do some discussion about that. So I go back to the SEO Space Environmental Report in the 2025. We could find that on the LEO, there's roughly 20,000 satellites in this kind of the orbit. It's much more than the other the satellites in the other orbits. So I will focus on the LEO, and there is another reason I will mention it later. Another thing is that because we want to discuss that is there any position could be accumulate the debris. I want to emphasize there is a spatial orbit, the geosynchronous orbit. while the satellites have already finished their mission, human will artificially push them into the outer orbit. They name it is a spacecraft cemetery. Although around this kind of the orbit, there's a lot of some kind of the garbage of the satellites, but this is not our main issue. I want to discuss is the naturally accumulated position. So this is a simple calculation for the basic orbit's behavior. Because I want to focus on the LEO, and the height or the altitude is roughly at 160 to 2,000 kilometers. Compared to the radius of the Earth, roughly 6,000 kilometers, it is quite a low position. So I will not consider any eccentricity. So this is the circular orbit. I can calculate the velocity of the circular orbit and then calculate the periodic. So it is the periodic for 4 different heights of the orbit in the LEO, and it is the cycles per day. So most of them are roughly 70 times, rotating the Earth 15 times per day. And the velocity is roughly 7.5 kilometers per second. Okay, so I try to do the simple simulation using the Ranjakuta 4 integrator. It is the, I think the simplest one to do the calculation and follow the equation of motion like this. And to be sure, the time step is much smaller than the time, the orbit, the periodic time. I set the time step roughly 10 seconds, so that's why I cannot stimulate the extremely long-term orbit. So yeah, that is a simple simulation result. Is if we just consider the rotation. Obviously, yeah, indeed, satellites will stay in some height. But do you think is it correct? We cannot ignore that it is an important factor. Is the atmosphere. The atmosphere, and then the atmosphere will drag by the Earth because the Earth have some rotation, and this rotation will drag the atmosphere. So atmosphere will have some uniform rotation similarly, and this kind of uniform rotation will drag the satellites in the LEO because the LEO is quite low compared to the other orbits. So I go back to check the density model of the atmosphere from these 3 different references. So this is the table I try to use. And this is the Earth's rotation. Then this is the formula I try to calculate the drag force by the rotating atmosphere. So considering this kind of atmosphere drag, we will find that, for example, if the initial height is roughly 200 kilometers, oh sorry, I forgot to mention, all of the orbit I stimulate is that once, if the satellites finish their work, so it have already broken and there is no any pulsation. So the initial velocity is straight parallel to the horizon. So consider the drag force, we could find that only need 6 days. This satellite located at 200 kilometers will re-entering into the atmosphere, that is drop on the Earth. So just a simple illustration for this simulation. Where is my cursor? Here. Okay. So obviously in the beginning, it seems that it is the stable orbit around the Earth. Okay, oh sorry, I exaggerate the length scale here because the 200 is quite small compared to the radius of the Earth. And while the time extremely close to the 6 days, you will find that first in the beginning just slightly deviate from the circular orbit, but in the end, it will dramatically drop on the Earth. So that is the influence of the atmosphere drag. So remember what kind of issue we want to discuss is that we want to know is there any orbit that the debris can stable located at this kind of area. So obviously, this kind of orbit should be above the influence of the atmosphere. Another interesting thing is that because the rotation of the Earth have the specific direction, so if the initial velocity toward the east or toward north or toward the west will cause a different drop in time, I just showing here. But the reason I want to do this test is I want to be sure this kind of influence will not dramatically influence the final result. So they only have roughly 10% difference of the drop in time. So let's see. I compare the different orbit with the different height for the 200, 400, 600, and 800 kilometer. Obviously, for the first two, for red one is 200, green one is 400. They will drop in roughly 10 years. But in the WALL-E movie, the time is roughly at 2,800. So if we want to see this kind of the debris layer, it should not drop in on the Earth in roughly 800 years. So let's see the orbit with the 600 and 800 kilometer. Because I don't have enough time to do the full simulation, so I just make the simulation and at roughly 80 years, we will find that at 80 years, the orbit with the height of the 600 kilometer, it have already dropped roughly 40 kilometer. So if we image that, I want to show in here. The figure showing here is that in the beginning, you will like a linear dropping and then will have a dramatically drop. So if we do the extrapolation for this kind of value, we could expect that the altitude will lower than roughly 200 kilometer, even though it is only the linear drop. So I do not believe that the 600 kilometer orbit can be stable or can be survived in the passage of the 800 years. So I want to have a first conclusion is that in the LEO, the orbit between the 200 kilometer to the 1,200 kilometer, only in the height of the 800 kilometer to the 1,200 kilometer. Within this area, we can expect this kind of the debris layer in roughly 800 years. So we know the rough range of this kind of the orbit. So we need to discuss, or I want to discuss that the collision probability, because as I showed in the beginning, although in reality, it have already been the 20,000 above satellites on the LEO orbits. So I want to know what's the collision probability. Why collision is important? Because collision will make the fragmental debris, and also it will rearrange the energy between the fragmental objects and change the orbits of them. So it's highly relevant to the distribution of the debris. So I didn't do the simulation because I don't have enough time, so I do the quick calculation. First of all, just start from the mean free path, and this is the mean free path is relevant to the number density of the object and the cross section, and then collision rate is equals to the relative velocity over the mean free path, so we could know how to express the collision rate. And second thing is that if we constrain the area of the orbit, for example, as we have the conclusion, something like a range between 800 kilometer to 1,200 kilometer, we could know the shell volume. And then we need the relative velocity from the different orbits. I should show here. From the ESA report, so far we have some common orbit with the different inclination. For example, low inclination, mid inclination, polar, and retrograde orbits. And I checked the report, so it roughly contains 10%. This is roughly 45%. This one is 40%. This one only 5% satellites. So using this value, we could try to calculate the collision rate. And the different direction, because I mentioned the 4 different orbits have a 4 different main inclination angle. That means we could know the relative angle between the different orbits. So we could calculate the collision rate on the different orbits using this formula. I think I need to ignore some detail. Okay. So using this method, I try to draw that for the different number of the debris objects, what is the collision times in the 800 years? For example, if it is roughly 5,000 satellites debris, this value is the rough value for the object on the orbit between 800 to 1,200 kilometers. So the collision, we can expect roughly 1 collision in 800 years. And if we increase the object number, for example, if the collision generate a lot of the minor debris, for example, in the 10 to 6, we can expect roughly 10 to 3, that is 1,000 collision times in 800 years. What that means? That is this Kessler syndrome is possible. What is the Kessler syndrome? That is if there is a lot of debris on the orbit, each of collision will trigger the much more minor debris. So while the total object number increasing, the collision rate or the collision times will dramatically increasing. So in the end of the Earth, we will expect that around some orbits, it will full of the garbage. So that is what debris layers show in the movies. So can we have the conclusion to say the movie is true? Let's try to go back to the snapshot of the movie. Okay, is it real? If you remember that I mentioned, if we just try to evaluate the spacing interval between the different debris, is roughly 10 meters. If we do the simple calculation from the volume of the shell between the 800 kilometer to the 1,200 kilometer, we will get volume is roughly this value. And then because we know the spacing interval is roughly 10 meters, so that means in each of the 1,000 meter cubic, we could find one debris. So the debris number will be 3 times, roughly should be 3 times to 10 to 17. It's an incredible number. If we try to use this number to calculate the collision rate, for example here, I'm showing here, the collision times, I show in 1 second because I want to do more discussion about that. In each 1 second, we will see the 1,000 collision. And the collision time scale will become extremely small. It's roughly 0.001. What that means? If we compare this time to the orbits, because we know the periodics of the different orbits, it's roughly at 1,000 scale, 1,000 seconds. That means once the satellites or once the debris haven't finished one period or one orbit, this collision have occurred extremely, it will occur very several times. So why this point is quite important? Because it will indicate that the motion of the satellites will not follow the orbit dynamics. Instead, it follows the random motion. So the motion of the satellite or debris cannot be described by our basic description. If we consider the random motion, that is, if we consider, for example, at each of the collision, the energy transform can simply to show in here. This is the elastic factor. I consider this factor is only 0.9. That means the roughly 10% energy dissipation for each of the collision. Although I have already used this kind of the conservative value, you will find that, and then I put all of the value I need, that the collision rate, the relative velocity, you will find that the energy dissipation rate is roughly this value. It is incredibly high compared to the kinetic energy at orbit of the 800 to 1,200 kilometers, roughly this value. If we straightly divide them with each other, you will find the debris on this kind of the orbit will drop in roughly 0.03 seconds. So this kind of orbit will not be stable in reality. So, okay, I want to mention this first. So the key feature of the debris level in the well-E, we can answer all of them now. The first one is the debris should not be stable. They have some moving motion. But yeah, indeed, can concentrate on some specific layer. And the second is that the typical spacing between fragments should not be 10 meters, because 10 meters will trigger the extremely credible random motion. And another thing is that, as we discussed, that it should have some catastrophic collisions. So we answer all of the in reality feature of the scenario in the well-E. So what can we expect for the far future? What's this kind of the debris layer should look like? That's my own interpretation. I'm not sure whether there is any reference or not, so I just want to share with you guys. If you have any suggestion, you can tell me. So, because the in reality part for the orbit shown in the well-E is that it should not be random motion if it is the orbit on the specific, if it is the dominant by the orbit dynamics. So there is the transition criteria. That is the time scale of the collision should roughly equals to the time scale of the periodic. If the time scale of the collision shorter than this one, it will become more like dominant by the random motion. So that is the critical value. So put all of the value we need into this relation. We can find that at least we need the several hundred meters spacing interval. That is roughly 500 meters. So what we could expect that in the far future, we could find some debris layer, and the spacing interval between the debris should be roughly 500 meters. So that's what we could expect in the future. Okay, that's all. I think I have mentioned all of the things in the previous. The most important thing I have mentioned, that is what we could expect in the future. So I just leave my conclusion here. Thanks for your attention.
Thank you. Very nice.
Thank you.
So any questions and comments?
Angel? Do you need this one or this one? This one. Okay.
Thank you. So how do your conclusions affect how we want to do space travel in the future?
In the future, if we do not have any schedule to clean the debris or all of garbage in the debris layer, we cannot do the space travel.
Impossible.
Possible. It will crush on a lot of the debris. Yeah. So that's why the ESA report is saying that it is an important issue. Mm-hmm. Yeah. I remember they mentioned this point several years. Yeah. Okay. Should we?
I was wondering in the simulation for atmospheric drag, you showed below 700 kilometers. That's 500.
Let me go back to the slide. I need to know which part you want to know.
Yeah.
Is this one?
I think we're talking about LEO, MEO, and GEO, different layers of. But anyway, okay, you don't need to show me a simulation.
Sure.
I was wondering if, if the atmosphere drag would act on the satellite, but if there were collisions between the satellite, and then the debris would be like screws and nuts from the satellites. Then the atmospheric drag wouldn't have much effect on those smaller objects. Right?
Actually, this drag, at that case, will change because I show the function here is the drag acceleration. So it is important factor is the drag coefficient is relevant to the cross section and the mass. So once it fragmented into the smaller or the minor debris, this value will change. So the drag force will also change. But I think, in my opinion, that is not the main point in the case of the collision, because the collision is actually. I don't think the kinetic energy will completely transfer to the minor debris. The energy will dissipate by the heat or by the material. So I will expect the velocity of the fragmental debris will much smaller than the original one. At that moment, because it have a lower velocity, the orbit will dramatically change. If it is lower than the 6 kilometer, it will dramatically drop on the Earth. Yeah, I think this is a more important thing. Sure.
Thank you. I think it's a sort of comment because I have seen that one anime called Dead Humanity, and it was about some groups that remove the debris of the around the Earth, and somehow they move it into Earth, and because of the atmosphere of the Earth, the debris would be burned, and it causes some light. And I think if they fall back to the Earth because of most of the debris around the Earth is almost aluminium, and it would be burned and don't damage the Earth.
Do you indicate that if they don't need to do anything, the debris around the sun will will re-entry into the sun? Does that correct?
I think the debris will be, if they fall into Earth, they will be burned.
That issue is relevant to the size of the debris.
Yes.
And another thing is that you need to make sure they will re-enter into the atmosphere, because the debris layer I mentioned is at roughly 8 kilometer to 1,200, and if we didn't have any other factor to push the debris back, actually the orbit will maintain for extremely long time. So you still need some artificial factor to force them back to the atmosphere. Yeah, but once they close to the atmosphere or denser region of the atmosphere, they will dramatically drop. No problem. Thank you.
Okay, thank you, Jeremy.
Thank you.
I'm sorry, but we're running out of time.
Oh, sure. It's
Is it
only.
okay to do the quiz next week?
Oh, sure. If you want.
Yes, we need it.
Okay,
I
okay.
should have
Yeah, it's fine.
finished my lecture earlier.
Don't
I
say it.
didn't have enough time.
I think I spent too much time.
Well, anyway, it was an excellent presentation. I liked you did the calculation yourself.
Thank you.
So thank you, Jeremy. Then let's continue next week. Let's start next week from with Jeremy's quiz. So everyone, please remember the contents until next week. Don't forget about it. Otherwise, our test score is going to be bad. So. Okay. So let's finish the class today. Next week I will be back. So see you in the classroom next week.
Okay.
Okay.
See you.
Thank you, everyone.
Bye bye.
Next week. Bye bye.